It's a pleasure and honor to be here sharing some of the thoughts I have regarding big data analytics. And before I start, we are a group which is very fortunate to have organizations like excuse me, National Science Foundation and Department of Energy who support the research that we do. And a lot of the work that I'm going to describe is a result of that support. And of course, various students and postdocs and the community that contributes to this. I was very pleased to hear Dr. Brinkman's presentation and his discussion about applications such as climate science and so on. And I would talk a little bit about that as well, particularly the role of data and analytics in understanding climate change. But that's an illustration of how we think about solving problems and leveraging data analytics for that. So first of all, this is not news to any of us, right? There is data everywhere, okay? And we must remember that data is not knowledge. Data is, it's a passive thing. It's a bunch of bits. Unless you do something with it, it's not of much use. So, but where does the data come from, okay? You will hear in the news all the time. Every time you use your cell phone, there is data generated. Any transaction you do, there is data generated. And if you use supercomputers to do simulations, there's massive amounts of data generated. So you can think of supercomputers. In fact, Dr. Hitchcock talked about this in one of the few presentations that I attended in DOE meetings, that you can think of supercomputers as instruments generating massive amounts of data. So the question is, what do you do with this data? Now, if you take social networks, Facebook or Twitter or blogs and so on, or social media, there's massive amounts of data. Now, of course, we use that for communicating with our friends and communities, but there is massive amounts of data. If you believe it or not, there are millions of tweets, for example, about drugs and their effects on various people. Can we use that data to understand? Can we think of that as a limitless focus group? Because that's data that can be used to improve healthcare, for example. So if we start to think about the domains in which we can apply big data and high performance computing together to extract knowledge or actionable insights which you can use for making decisions. If you think about, look at this part. These are science magazines and science journals, and they have special discussions, special issues on data, right? It's very recent phenomena that entire journals are dedicated to, or issues are dedicated to that. Of course, there is massive amounts of data, and companies are using that and would like to use that for business decision making. Science, you heard about LHC. There are telescopes generating terabytes of data every day, and of course, supercomputer simulations. So how do we take this and apply our knowledge in applications in high performance computing and generating techniques for understanding? So one of the things that I like to do is to differentiate what it means, what is a data intensive computing versus what is data driven computing. And the reason for that is that data intensive computing has been around for a long time, right? If you are a processor designer, if you have lots of misses in the, if you have a lot of communication off chip, you think of that as data intensive computing. So data intensive computing essentially refers to a lot of data movement, doesn't matter whether it's going to disk or over the network and so on, as compared to amount of computation you might do, okay? So that's but that's not data driven. You're not using data to derive knowledge from that. That is what many people, including myself, call data driven computing. So simplest way to think about this is that you get some bunch of data on an Excel spreadsheet and you start to derive some information from the data. But the data is what is driving the computing, or data is what is driving. That's the first step. If you didn't have that, you have nothing to compute or nothing to discover. Now, within that, you can have big data, you know, the Walmarts of the world in business world, or astrophysics and large simulations. So it's a bottom-up process. You start with the data and you try to figure out if there are actionable insights. Furthermore, what this allows one to do is to leverage. So for example, let's think of a bunch of simulations that have created petabytes of data that is out available. Now, thousands of researchers like you and us could use that data and analytics technique to leverage that and multiply the effect of knowledge discovery from that. So that is what is enabled with data-driven computing. But when you think about data-driven computing, you have to think about that it's not a it's not a transactional process. In other words, when we think of simulations, we say, okay, you start, you know, you have initial conditions, or your data is, generated, or your meshes, or what have you. You do a simulation and you generate a lot of data, and then you do visualization. But that's one transactional process, right? There's no relationship to 1,000 other things that are being done. So that's the generation phase. If you want to, at least in my opinion, if you want to use data-driven discovery approach, one has to think about the entire ecosystem, right? For example, it could be as simple as I'm doing this simulation, or I'm generating this data. How am I going to use it in the future? And if I could use that knowledge, I could optimize even just the process of I/O and storing the data so that it's useful. So for example, I may just go from a spatial domain to a temporal domain because I look at data across time. And that results in developing techniques in data reduction, managing data, querying data at large scale. Okay, and there is a lot of work going on. And then once you have this data organized in, and I'll illustrate this through a climate change example, then you want to understand from this data any actionable insights, right? So for example, do I find a particular anomaly in this data, right? So that's your trigger or question, and you analyze this data to do maybe predictive modeling or anomaly detection and things like that, okay? So this is, you're starting from here, you're going through, and then from understanding the results, you refine and you enable this process. So in computational science world, we typically do not spend a lot of time thinking about the entire cycle, but we spend a lot of time this. But if you want to enable and understand this entire process and use it for furthering the discoveries, we have to think about this ecosystem. So here are some illustrative sizes of data. It's not, it's probably a year old, maybe a little more. So what I'm going to, there's again a bunch of applications, massive amounts of data. Okay, so I'm going to talk a little bit about climate science and how you use data-driven approach for understanding climate change. That's one. And then I'll also talk about how to relate this from, how to go from science to social, for example, and how could you use similar techniques from massive social data sets for various applications. Okay, so in fact, I don't need to spend much time on this. We heard an excellent talk in the morning from Dr. Brinkman, and one of the things that is important, that climate change is important, of course, okay, but the way to think about, is not only the bigger picture, right? Bigger questions, okay, temperature is going to go up by a degree over 50 years, but how do we get to actionable predictive insights? In other words, could we use this to manage situations, to develop policy and things like that? So there are applications, I mean, there are things like fires, or we heard about the melting of the ice caps and things like that. And you saw a chart very similar to this earlier in the morning, that if you, so this is a big picture chart, that if you take natural forcings, then in fact you see this blue chart, I mean blue line, but if you take all forcing, then it goes up like this, which is correlates with observation. In other words, it's the human-induced effect on this, right? So the question then for us is, as many of you are working in this domain, but anybody working computational science, is that we have physics-based approaches, right? We model, we use mathematics to model, and then we do simulations and validate our hypotheses and models and try to understand results. Physics-based models are essential, right? But that's one component. One of the, this is from Nature. The sad truth of climate science is that most crucial information is the least reliable based on those models. In other words, it's very reliable for global scale, big picture results, but it's least reliable for variables that are crucial for impact, regional assessments, things like that, right? Hurricanes, extreme events, and things like that. So how can, what are the examples of those? So for example, trying to predict hurricanes, the paths, whether they're going to hit landfall and things like that, or maybe outbreaks of diseases. So there is a high correlation between the type of climate you might expect in certain regions and, in this case, meningitis in Africa. Or based on the genesis of the coast of Africa, genesis region for hurricanes, for North Atlantic hurricanes, whether we can predict if the hurricanes are going to have landfall or they'll go back into the ocean and things like that. So these are extreme events. The question is, can we use data-driven approaches to understand that? Now, in order to do that, go from A to B, we have to take the data, and what this shows is the ecosystem that I talked about, how that is applied. So whether you take observational data, which could be massive, or simulation data, but many of those, right? That's a spatio-temporal type of data. So you have space, of course, and then time associated with observations or simulations, and of course different types of variables, sea surface temperature, pressure, etc., etc. So this is your, you can call this as your transactional part of data generation, data collection, and things like that. Then this is a transformation of understanding what is the useful data, processing of data, or pre-processing of data. So this shows anomaly time series at each point. What this computation essentially entails is understanding whether at a particular time, is there an anomaly, difference from significant difference from a normal behavior, right? Now there are millions and millions of such points, and you find those time series and so on. Now you find across the globe, in this example, whether there are similar phenomena. Okay, then not at local points but across, because local data is highly correlated anyway. So what that does is, that type of approach takes this data and transforms that into something called, in this climate network, right? In other words, you could have a point here and point here which exhibit similar behavior. Now if you want to think about what this means is, when we buy something, let's say from Amazon.com, right? It might say people who buy A, beer, also, beer is not a good example from Amazon. We don't buy beer from Amazon, right? Okay. Maybe people who buy thrillers from this author also buy bicycles from this type of brand, right? There is no relation, there is no hypothesis there. It's discovery based. You know, one person who's buying thrillers or group of people who are buying thrillers maybe 25 to 35 years old, and people who are buying bicycles maybe 50 years old. So there is no relationship. You cannot imagine those, right? It's a similar situation here, that you may have you know, a point here and point here across the globe, and they may be highly connected, right? So call them teleconnections and so on. Once we have this graph across the network, now the question becomes, can I find motifs or patterns which are associated with extreme events and which are associated with normal events? So now if I could analyze this massive amounts of data in this, then when in the future I have a trigger. What is the trigger? Hurricane being formed off the coast of Africa, and 15 days later it's going to approach the US coast and so on. So that's the trigger event. In Amazon example, what is the trigger event? When you put something in your basket, right? That's a trigger event that says, okay, a rule or some mining is triggered, which will give you an actionable or recommendation. So that's so what you're doing is you're looking at extreme phases, what are the motifs and so on, and normal phases, and then trying to do prediction. So it's the entire ecosystem where you start with the data, transform, do data pre-processing, querying, et cetera, transform it into different, and then a different model or different representation, and then do your predictive analytics and modeling and so on to answer questions such as hurricane frequency, for example, or any other extreme event, or whether when the hurricane is formed, is it likely to strike the coast, or is it going to the Gulf, or it's going to fade back into the ocean? Okay. So this is the entire, so to speak, ecosystem there. Here are some examples. So based on data from maybe 50 years, it shows that and window of decades from observational data, that there is a sort of oscillation on the data in the climate networks. Higher edges means stronger connections, lower means weaker connections and things like that. With long distance teleconnections, what that means is that for example, here, stable teleconnections between 3 regions, which is off the coast of South America and Indian Ocean and things like that, right? They are very far apart, but you can see those connections. What this shows is a discovery-based result, which is already known, right? Because you see that there is a desert here. So taking the data and saying, okay, let's see what this looks like. What this shows is that the Sahel region is part of southern Africa, okay, which is green and things like that. And then you can sort of deduce and you can observe its transformation from green to being part of the desert. Okay? And it's discovered by data analytics. Of course, it's validated because we can observe that today. How about forecasting hurricane tracks? So you have, the way it is done today is you use physics-based models and large simulations and things like that. And there is a certain error rate. So 48 hours, beyond 48 hours, the error is around 185 kilometers and so on. The question becomes, what if I have historical data of 60 years, let's say, right, of all the hurricanes, all the observations when they are formed and how they move, okay? And if I could take this massive amounts of data and understand that process that I described, and then predict with certain accuracy what type of hurricane it is going to be, then when a hurricane is formed, it gives me 15 days to make decisions with certain confidence, right? And but what unlike immediate simulations, what it's doing, it's leveraging historical data over 50 years. So using that, I should point out, by the way, this work is collection of work by us, University of Minnesota, NC State, and so on, who are part of a big project on data-driven understanding of climate change. And what that shows here in this very quickly is that you can get pretty high accuracy in predicting whether hurricane is going to strike the coast, go off in the ocean, and so on. Now you take this problem and then you can make it narrow. Okay, so for example, if you take North Carolina, right? So now the question for North Carolina is, remember in the data discovery domain, the problem is a 3-class problem, so to speak. Is it going to go to the Gulf? Is it going to strike the Atlantic coast? Or is it going to go back into the ocean? Now for state of North Carolina, the question may be a 2-class problem, which is it going to strike North Carolina, or is it going to go somewhere else? Then it's not my problem type of thing, right? So, but for Florida, it's the same question, right? Et cetera, et cetera. So now you do more and more regional analytics. Data is the same, 60 years worth of data and so on, but now you have huge number of so-called problems, and then you start to see how accurately can you predict. And if I can predict very accurately, I can make certain types of decisions, investments, and so on, way in advance, which of course is good for everyone. So now, if you take current data and then you say where it's going, if you go from coupled model intercomparison product, which is a project which is CMIP 3 to 5, if you go from here to here, this is the impact in terms of the data growth. So an order of magnitude increase or a factor of 2 to 4 increase in each of these results in data going from tens of terabytes to tens of petabytes. And all these analytics and so on cannot be done without high performance supercomputing and things like that. So, so we think about supercomputers and high performance computing mainly used for simulations and so on, but as we move forward in computer science, computational science, and others, we start thinking about how to use these massive instruments and massive systems to also derive knowledge from data. And that, for those of you who may be interested in computer science or scalable computer science, there are many, many challenging problems of data analytics, relationship mining, understanding complex patterns, understanding complex networks, and so on. And this is crucial. And the way I like to think about this is that if you've heard of the phrase needle in the haystack, right? A lot of the approaches, what they do, they're statistical sampling, right? So when you do sampling, and if your needle is not part of the sample, then you will never discover that. So therefore, algorithmically, you have to design algorithms that work by design on big data, not reducing it and then working on that. That's an important consideration. So what about social? So that was an example. In science, you can map your application into that. If you take that picture that I showed earlier, right, you have billions of people on the globe. They are all communicating with each other, right? So they are interacting in space and time, right? Space, somebody from US communicating with somebody in London, right, et cetera. So, and time, of course, over a period of time. So you can think of it's a spatial temporal problem. Similar, as I gave an example, similarity of interest defines communities, right? People who like to climb, right? That's a community. People who like to play soccer, community, et cetera. So, and communication is across the globe, so it defines your teleconnection. So you can very easily map the science problem into social problem. So then, from this, a company might want to understand, let's say, Coca-Cola, or that what are the connections of my fans or customers or people who really like Coca-Cola. Or a politician may want to understand what are the people's interests who are engaged with me, and so on. Okay? So I'm going to use an example, and if you want to try it out yourself, you can go to this website called pulseofthetweeters.com, and you can what I'm talking about, you can try it out. Okay? There are hundreds of billions of tweets and being analyzed, including top 200 diseases in the world, top 200 drugs, what is the discussion, who's influencing the opinion, and so on. So I'm going to take this example and show a real application. I mean, I'm sure how many of you know about Twitter? I should ask how many of you don't know, but nobody will raise hands then. Okay. So there are two, if you think about, so the way Twitter works is I tweet, and if you're following me, you'll see a tweet. You see the tweet. Then you can forward it, respond to it, etc., etc. So there is a static part, which is me and my followers. That's like your address book in email, right? So if I have 1 million followers, right, all 1 million have the potential to see the tweet. Doesn't mean they see it or they care about it, right? So that's the static network. Then there is something called a dynamic network. Every time I tweet, a lot of people see it, more people see it, and more people take action, higher my influence. But that's a dynamic network, right? Only it's formed when something propagates and somebody responds. So, for example, if Ashton Kutcher tweets about LHC collider, discovering boson, Higgs boson, I don't think anybody is going to care about it. But if he talks about Hollywood gossip, maybe somebody will care about it. So the point is that the response is very dependent on the context and the influence of that particular person. And that can result in understanding the influencers. And so, for example, I talked about two topics. So even though in this case, if you look at Y here, has 6 followers, right? So you will say, okay, static network, this guy is more influencer than X. But for a particular topic, a lot of people following X tend to respond. Then for that topic, a disease discussion or politics discussion, this person is more influenced. Now you scale this to billions, and then that's your scalable problem. I'm going to give you an example of its use. In fact, the pulseofthetweeters.com, which is something that we released in the public domain for people to use. And this is a real application of that. And if you want to know, there is an article in Communication of ACM recently on this that we wrote to describe how this works. And I should point out that what you're going to see here was not an organic, I mean, it's not, so we are doing this analytics of tweets and the networks, but we didn't think of this result on application. What happened was that I was in my office and I got calls from a lot of journalists saying that when this event was happening, they went to this pulseofthetweeters.com, and that was one of the few places where they could understand what was really going on and who was influencing the opinion. So they said, okay, we might as well write about this. So as you know that in the Arab Spring, Egyptian revolution, by most account had social media played significant impact. So a significant role. There are a bunch of topics, people talking about Egypt, Cairo, Hosni Mubarak, and so on. What I would like to just to show here is that the top influencer was Al Jazeera. There's no rocket science. This is probably understandable. And within that, specific journalists and things like that, CNN. And there was a high correlation about coverage on of the news on ground as well as in the social media. What is interesting here is this. This is an independent journalist with only 300 plus followers, whereas the CNN has millions of followers. But Mona, she was highly influential, it just showed up from the network. And because of the dynamic network part. So if you look at this, you can see the events unfolding and the corresponding impact or vice versa, because maybe this is indicative of what's going to happen here, right? Of course, this was, so if you in the beginning, January 25th, only Cairo is trending, okay, and there are lots of negative tweets, so it's corresponding sentiments, 4-1, and so on. And these are the different events and that are reflected in the corresponding tweets, right? For example, in this case, huge increase in tweets on Tahrir, which is the Tahrir Square, where there are a lot of demonstrations and people had occupied that, okay? And when the vice president resigned, etc., there were a lot of positive tweets and so on. So you can, if you were observing this, you can predict these events and vice versa. So then you want to understand is, just like we were talking about motif, right? There are different patterns for extreme events versus normal events. So in this case, if you define normal events where people are following politics, entertainment, sports, and so on, how does this behavior of this, we can call it this event of Arab Spring, does it differ? And if I can understand that, yes, it differs, then my models can try to predict from this massive amounts of data in real time whether something different is going to happen. So if you look at this, in each of these categories, there is a significant difference from the norm in all these other topics. So whether it's the number of followers, tweets, how fast it goes in the network, negative sentiment, user sentiment, okay? So now in the social space, what you have is a norm on different types of activities, and now you can see what's deviating and then try to predict or use for any other purposes. So let me give you a couple of interesting nuggets. This is based on 150 million users. I'm not saying who I'm voting for or following, just an example here. So there's, as you know, that social data is playing huge amount of role in politics these days. So there's massive amounts of data. If you look at Barack Obama, he has maybe around 25 million people on Facebook who are following. Mitt Romney has maybe 4 million, and so on. So if you look at the networks of connections out of billions and billions of possibilities, first you will see that people who are engaged with Barack Obama, okay, here, are heavily engaged with Maya Angelou, who's a poet, with Michelle Obama, etc., etc. You see here, this is MSNBC. Okay, that's a TV channel. So people who are engaged with them are engaged with this. Whereas you look at Mitt Romney, the network connections show, for example, Mike Pence, who's a congressman from Indiana, Marco Rubio, Bill O'Reilly, which is Fox, etc. So you can see, you can discover patterns. It's not top down, it's bottom up out of billions of connections. So now the question, you can reverse this and say, hey, I would like to reach out to people who are similar to who are engaged with me, because that's how you grow your customer base or your voter base, etc., etc. So now one can start to target these micro segments in order to develop business or anything else, or develop understanding. So that's the point of this. This is similar data from Twitter, and I just, for very interesting result that again discovery we found. So when it's going on, when the primaries are going on, you see that this is a community detection, same network connection. You find anything interesting here? Let's see if you can read the slides. I'm pointing to it, come on. Papa John's, right? So, you have all these politicians. So can anybody think why that may be the case? Sorry? I didn't hear. You know what Papa John's is, right? Yeah. What this says is that people, you know how people work in different campaigns. They are 24/7, right? and all they do is eat pizza for breakfast, lunch, and dinner, right? So they are all following Papa John's, just in case there is a promotion and they get $10 off or whatever, right? So they are all following, and Papa John's is promoting their products. So in the network, it shows up as highly connected with Papa John, right? So if you look at connections of the search engines, Bing, Yahoo, Google, you will see that number 6 is George Foreman cooking, connected to Bing. So when I was presenting this to Bing people, they said, we don't believe this. How is that possible? And I said, you didn't ask me that question about number 1 and number 2. And they said, but that's obvious. So I said, if it's obvious, you don't need to do any mining to figure out the non-obvious ones, right? Then I asked the following question, did you design Bing to be used only by people who are technical? Or you want, mom who has George Foreman cooking grill to find recipe using Bing? Maybe your Bing is good at giving good recipes for that, right? So the point is that there are connections that you don't know which can be used to discover this knowledge, which then become actionable. As you can see, Google's users are highly technical, whereas, and there is a common connection between Bing and Yahoo about the type of users here. Okay. So I was talking about drugs and diseases. So here is an example of, we were talking to Abbott Labs, which is a big drug company, and of course they develop a drug called Humira for arthritis. And we said, okay, let's say in the social media, there are hundreds of sites, organizations, thousands or tens of thousands of people discussing those drugs, the disease, the side effects, the problem, policy, et cetera, et cetera. And it just sort of bubbled up, right? So for example, these are comments by people in policy-related, weather-related, depression-related to the use of drugs, the cost of drugs, et cetera, right? So a lot of people, there is massive amounts of information which a doctor doesn't know, the policymakers don't know, the drug discovery guys don't know the side effects and so on. And this is just one example, right? So so that's an example of where you can use this massive. You don't know what you will get. So then you take the next step and say, just like we think about a picture is worth 1,000 words, could we say, can we move to a point where data-driven discovery becomes 1,000 simulations, right? If I already had 100 simulations and the outputs already available and observational data, could I discover information by combining these together and using that ecosystem so that I don't have to do other 1,000 simulations? Maybe the result already exists out there, right? And this is an example of exactly how that works. So we are collaborating with some material scientists. And what we did was we took simulation results of around 10,000 materials and compounds that were simulated. Used all this data and say, let me throw a random, N2O2, some random combination, right? And see whether it predicts whether it's going to be stable or unstable compound, et cetera, et cetera. And with 90% accuracy, we were able to predict which category. So now you can think about this is that I can use it to prioritize. Instead of doing 100 simulations, I can do maybe 10 simulations because I can prioritize which ones are the important compounds and so on to simulate and further validate or investigate and so on. So it could be first step to prioritize what you want to, how you want to move forward in your discovery process or in your science process and things like that. Okay, so in summary, all of us, computer scientists, computational scientists, applications, high-performance computing, the message that I have for ourselves is essentially, can we start thinking about how to leverage the massive amounts of data in all these domains to discover or accelerate discovery in science, whether it's natural science, social science, and so on, or maybe medicine. And there are a lot of exciting opportunities to do that, given we have high performance computing as well as data that is available. With that, I'd like to thank you for the opportunity and take any questions you might have if you have time.